Good evening. Welcome to this Convergence Science Network event and to the Bio 21 Institute. My name's Luan Ismail. I'm the founder and convener of the network. It's a great pleasure to see so many of you here this evening on a pretty cool Melbourne night. It's difficult to avoid the tsunami of news on AI, artificial intelligence, which most likely will be the next big thing in technology. It will disrupt the products and services of many industries, deliver unimagined benefits to society, and also threaten and upend some occupations and change the way we work. Not surprisingly, much of the content that we read and see about AI includes hype and misinformation, as distinct from what I would call trusted information. But what if we had a deeper insight into how AI actually works and how it delivers outcomes? This evening we will have the opportunity to do just that, examine how AI is delivering positive outcomes in healthcare from two leading and respected practitioners in the field. I'd like to invite our first speaker, Dr. Stefan Harrer. Please give a warm welcome to Stefan Harrer.
I'm pleased you invited me back. I thank you all for turning up, and I hope we'll have an exciting evening together. I really would invite you to come up with questions and be candid about them and come out with them, because discussions are much more exciting and insightful than me lecturing. But there'll be a couple food for thought ideas out there which I want to go through before the Q&A. This is certainly what it feels like. So Luan made that point earlier. We see a huge AI hype all around us, right? And it seems to have gotten to a frenzy where everything and anything under the sun gets an AI sugar coating over it, and thereby is miraculously made the hottest thing since sliced bread. Of course, we have to be a little more distinct in this. So without giving you a lecture on AI and neuroscience, I still want to make sure that we're all on the same page when it comes to what we mean when we talk about AI in this context. Intelligence is a real complex beast, and I want to boil it down to a bit of a hand-waving description, which every real neuroscientist in the audience would beat me over the head with a big stick for, but it helps to visualize the essential parts of intelligence and also artificial intelligence. So there's what goes on in the left brain hemisphere, which is often referred to as the emotional, the creative part, imagination, artistic abilities. The other half runs logic. There's analytical thought, objectivity, language. And it's the two halves of the brain together that define some of the hallmarks of intelligence. Not all of these features is what we are going to be talking about today. They're not also equally strongly represented in those AI technologies that we find in health and medicine. The ones that we'll focus on tonight are emotion and creativity, believe it or not. And there's also, of course, analytical thought and language and logic, recognition of patterns, and so forth. Now, I said there is this AI hype, right? But AI did not just magically descend upon us overnight out of left field. It's coming with a profound history, right? Back in the 1940s and 1950s it started. It went through many near-death experiences, some of the recent ones in the 1990s, the early 2000s, and also through as many rebirth and hype cycles. So that's something to keep in mind, right? If it seems to you like now AI is everywhere, and where was it like a year ago? That's a very distorting perception of the history of AI. It is the reasons for this are different. The reasons for this recent hype is that AI has gone from something that's called narrow AI, where very specific features of these intelligent cognitive capabilities were used to solve or attempt to solve very specific niche challenges in specific domains. And scalability beyond these wasn't necessarily there. And AI has gone from that state to what we call broad or general AI. That is a type of technology that allows you to essentially confront your AI system without having to upfront calibrate it much or custom design it, challenge with questions and challenges from a variety of fields, different types of problems, and with some limitations, and of course yielding different performance, the AI will be able to tackle these individual questions. So that's why someone who has a problem summarizing a huge amount of documentation can now come to the same type of AI that someone who is looking for tumor segments in a mammography image, right? And of course there's some things you need to do, but that breadth of applicability that we're about to see and that we have embarked onto is really the reason why you are really seeing this AI topic being all around you in everyone's mouth, and everyone has something to say about it and has possibly also an experience in using it. Now, again, as I've said before, we're not going to go through the history of AI here. Two things I want to point out. There's deep learning down here, and we'll hear about this. This is by today's standards, almost become a legacy AI technology. And what we're really seeing right now at the forefront of AI is we see what's called generative AI and large language models in particular, AI that is combined with quantum computing, and AI that can actually exhibits advanced reasoning capabilities, is on the verge of being able to make attempts of planning, and of course also explainable AI, right? So these are some of the areas that we see at the forefront, at the frontier of AI development right now. They're not overriding everything that has happened before, but they're really those capabilities of AI that allow us to tackle problems that we haven't been able to tackle before. This is something that I like to just really highlight because it's so true, and we often forget this, right? Humans tend to project what the future brings based on what we have experienced in our lifetime, and we extrapolate linearly, right? So there is what we might have seen over the last 2 years, over the last 5 years, last 10 years, maybe even more, but consistently we will vastly underestimate the degree of progress that a technological field of innovation will undergo in the immediate and foreseeable future. It's not a linear curve that we are expecting, that we should expect. We should expect a hockey stick curve. And in that sense, what we are seeing around the development and progress around AI right now is, in one way, seems unexpected and fast to us, but is really just a development that we've seen so many times in other fields of technology before. It's just right now in front of us, and is very much in our face. So, this pace will only accelerate. What will also accelerate is the pace of adoption of AI technology. Now, what you look at here is a graph that shows you how long it took for the telephone landline, for the refrigerator, for color TV, the microwave, technologies that we take as granted to really reach that level of penetration in our everyday lives. And that took often decades, right, for this saturation state to be achieved. Now, smartphones, social media technology seems almost like a vertical line on here. So that will be an experience that you've all had, right? Smartphones weren't there, and then all of a sudden, within a year or a year and a half, almost everyone seemed to have one. Now, the latest craze, ChatGPT, went from 0 to 100 million daily active users in 2 months. So it's got to be the most successful product of all times, right? Why am I showing you this? And especially in a clinical environment, the progress of the technological innovation plus the speed of adoption is so fast that it cannot be halted, right? These calls for bans of AI that you will have seen, completely unrealistic, also not productive, but it's a different story. So the only way to deal with this is really to get up to speed, to understand what this technology cannot do, the challenges of it, the opportunities of it, and then try to be a responsible part in the chain that progresses this technology into adoption. We can guide this, we can help contribute to the development, to the adoption. We cannot stop it, right? And also, personally speaking, with my inventor's hat on, I don't think we should stop it. We can talk about that over the reception. I think there's way too much groundbreaking potential in doing extremely exciting, helpful, productive things with this technology. But we need to make sure that it's going that way, because there's nothing more destructive than big screw-ups in either rolling this technology out in a not responsible way. You will all have heard about data breaches. There's, and I wrote about this extensively, and there's also some references at the end of the presentation. Right, the responsible development is incredibly important, and especially so in healthcare and the life sciences, where you find probably the highest stakes that you can have, people's wellness and well-being. Right, so that's utterly important, which is why we need to take a factual, measured, guided approach to bringing this technology into the hands of those who intend to use it and benefit from it. Clinicians, patients, these are all stakeholders that need to be convinced to use, to trust, and to adopt this technology. How do you convince them? Well, by demonstrating very clearly that there is value in using this technology to everyone involved. It might be an efficiency gain, it might be improved outcomes for patients. There's got to be some of that. Just because something is cool and allows you to do something is not reason enough to do it, right? And it will be even worse than that. If you, and I've had front row seats to this kind of experience several times in my career. In healthcare, particularly so, data science and AI. If you screw up once, you lose the trust of your users, of your clients immediately and profoundly. Getting a second chance of regaining this is extremely hard. So it's very much to be advised, to be cautious and responsible in the first place, rather than in Silicon Valley style, move fast and break things. It does not work in healthcare, right? And particularly not with the kind of technology that's so impactful that we're talking about here tonight. So I threw this slide in. There's way too much text on there for something I would usually talk to, but I understand we'll share the slides afterwards. And what you find on that slide is essentially what I would regard as a comprehensive overview of where in the health and medicine domain AI and specific types of AI make a difference. Important, this is everything you find on here is in one way or the other, to certain maturity levels, already in practice, okay? So that can be an early stage validation study or an FDA approved product. But none of this stuff on here is a castle in the sky, right? So we are really have this adoption curve in mind about real people testing, developing, or deploying AI-driven technology for these kind of tasks, spanning everything from the research and discovery side of things. We can discover new drug targets using AI, design new targets, to designing clinical trials and validation studies in more efficient ways using AI, then even the manufacturing supply chain of of drugs is impacted, as is the launch and the commercial part of bringing medical solutions to patients. And then there is, of course, and this is what we'll be talking about today, there's the diagnostic prevention and treatment area, where we'll see a lot of these AI-driven technologies as well. So I'm not going to talk to all of these. The three use cases that we're going to go through they're all in the diagnostic space, because Luan ran a pretty tight ship. She said we're going to be talking about diagnostics tonight. So this is the reason I would love to talk about many others of those as well, but these are really interesting ones, and they come from the diagnostic space. Digital disease diaries is essentially a technology that refers to monitoring patients over time and logging disease episodes of interest automatically using AI. Why is this important? Because AI, and this goes back to what I mentioned before, its specific feature of deep learning is something that finds complex patterns in big noisy data automatically by itself in real time. So this is where we can actually build patient monitoring systems that analyze data that comes in real time, and then log, recognize, and learn how these disease episodes look like in the data for that patient, and keep those records in digital disease diaries. Very important for example, running clinical trials, detecting endpoints, monitoring adherence control, assessing dropout risk, and keeping patients in trials, but also really making sure that treatment plans stay on top, that the outcomes of treatments are monitored, adjusted as diseases change. So these diaries are extremely powerful tools that complement assessment through other parties. We will look into EHR management platforms a little bit, and that's where we'll touch very briefly on generative AI. And then there is patient monitoring and screening techniques. And these are, of course, as we all know, part of everyone's daily life in one way or the other. There's regular tests we undergo, screenings that we do, that very much determine our own trajectory as patients sometimes just preventively, that can be assisted by AI technology to increase the chances of recognizing something that should be detected before it gets overseen. So these are the three use cases that we're going to be going through. The overarching theme, and I can't stress this enough, of all of these is the role of AI as an assistive system for human decision makers, right? AI is not there to replace humans in no point of this chain. It will only replace those humans who don't learn how to use AI. This is important. There's nothing to be feared here, only things to be understood. And this is actually not me, this is Marie Curie. So she said that, and she said, now is the time to understand more so that we may fear less. That is really where we are at this point, okay? AI is not coming for anyone's jobs. AI is a real powerful tool that we can learn how to use. And that will be how we look at all these use cases and the role of AI. We ran a study back in my IBM times, a large-scale study on the following, that was testing the following thing. So there were two massive data sets of mammography images, a US one, a Swedish one. These were X-ray images, and they were labeled. Essentially, there's a tumor here, there's no tumor here. Now, the hypothesis that we tested was, well, is AI, an AI model, an image recognition model, plus clinician reading, is that performing better in terms of recognizing the accuracy with which it recognizes tumors in images? Is it better than if the clinician alone would do that, or if the AI alone would do that, or is it not? And so we ran, and this is a disclaimer up front, right? This is a classical retrospective study. It was, at that point in time, 2 years ago, the largest study of that kind, and it used a plethora we ran it as a crowdsourced challenge, over 1,000 teams from all over the world that developed models there. And so the outcome of this study, to cut a long story short, was that in certain scenarios, not in all of them, so it depends on whether, it depends, and we'll get to that on the next slide, how AI is incorporated in the workflow of clinicians, of radiologists. But there were scenarios in which we found that AI plus the clinician would outperform what either one of them, the clinician by themselves or the AI by themselves, would achieve in terms of recognizing tumor segments in X-ray mammography images. So that was an interesting finding. It actually supported that hypothesis that I just put in front of you, that it's the clinician using the AI that performs best. That actually there's some truth in that. Of course, what we knew is that any of these findings need to be actually tested in the clinical operational environment that they're intended to be used in. And so I was very pleased recently, very recently, there's 3 studies here, they're all published either a week ago or a few weeks ago, that looked into that looked into different scenarios in which clinicians, radiologists would use an assistive AI system for reading mammography imagery. And the outcomes are something worthwhile to have a closer look at. Truth be told, these studies are also very intensely discussed. And they all have their limitations and open questions. But the baseline here is this, right? The top one that you see there essentially confirmed what we had postulated in our study, that if a clinician uses that AI system, they will be more efficient, they will be faster, and there will not be a diminishing performance in recognizing cancer. Okay, that's great. That's something that everyone would like to hear, that everyone would expect to hear. That is what we've all said AI is supposed to do. The second study, done by MIT, came to a very, very different conclusion, right? So these folks said, look, if there is actually an AI system there and a human uses it, it will actually perform less efficiently than either one of them would perform by themselves. So they came to the conclusion, said, okay, make a decision up front on which images you assign to a human clinician and which images you assign to an AI system, and then let them do their thing, and that's the best scenario according to our outcomes. It's very different to saying, let's have clinicians and AI work together. And then the third study is sort of that's the one in Nature, came to another interesting insight that says, yeah, okay, if there is an abnormality in the system that the eye detects, a clinician will look much longer into that specific case than if they had just looked at this image unassistedly. And that slows them down dramatically. And so, there's a real, inefficiency in doing it that way, because there wasn't a gain there in terms of the accuracy with which something would have been detected. So put all these 3 studies aside next to each other, and there is no, at least not to the best of my knowledge, this is all highly controversially discussed right now. But the point that we can get out of this is, it matters a lot on what we're trying to achieve by using AI. Right? That needs to be defined up front. What is the value that we want to add? Do we want to be fast? Do we want to be more accurate? Is it a combination of both? What resources do we have at hand? And it matters tremendously how you then incorporate the use of AI as a tool into the clinical workflow. It matters, for example, in our study, if you're comparing yourself to a double reader scenario, for example, in Sweden, there were the standard of reading is that there's a double reading of mammography images by 2 clinicians. In the US, it's different. So are you comparing yourself to 2 clinicians looking at that, or to 1 who would then use an AI system on top to reach the accuracy of a 2 clinician reading scenario? All this is important. So there's no one-fits-all approach here, and claiming success is a finicky thing to do because you have to really call out what the criteria are that you're using here in terms of using your AI system. We did the same thing with EEG data. In epilepsy, as some of you here know, it's a highly individualized disease. It doesn't look the same in each patient and even changes over time. Getting medication right and in the first place, and then keeping medication plans efficient over time is a moving goalpost problem. So this is the digital disease diary part where we find ways to monitor patients' brain activity in form of EEG signals over extended periods of time, and automatically need to detect these episodes of interest where seizures strike in these signals. That's an extremely time-consuming thing to do, going through these EEG traces, as neurologists spend like hours and hours on end doing just that, like really scanning through these EEG traces and putting labels in, annotating these, and say here's a seizure, and so forth. Wouldn't it be nice if there was an assistive system that would do a pre-selection and only presented a pre-selection with the same accuracy that a human annotator would achieve, and then only presented those cases that are borderline or within a certain, with a certain range that's being defined, to a human annotator for cross-checking. That's what we did in that study. And we found, and this is another retrospective study, that by running an AI model that is trained to recognize epileptic seizures in EEG data and applying that model to EEG traces that were collected from patients, and then using this AI model to pre-select and detect automatically epileptic seizure episodes, we postulated that in doing that, we could reduce the workload on human neurologist annotators by factors up to 100. That's being validated through, as we saw right before, through clinical studies right now. And again, with the mammography study, it will be really interesting to see how this method is actually, how this AI model is used by humans. Is it adding to the workload through some reason or some unforeseen factor that we haven't seen? Is it actually delivering on the hypothesis that we had put out there? We'll have to see. But this is the kind of scrutiny that needs to be applied to every and each one AI model that has been developed and tested on retrospective data, where oftentimes you see researchers sell it as if it was like a tool that you could now readily sell and use in clinical environments without further testing. It's absolutely not true, and it's very dangerous to make these claims. There's got to be a very thorough clinical, operational validation and testing phase and refinement phase for any AI model, just to test whether it's actually practicable and whether it delivers value or not. And that, in the end, will determine whether it's being used and valuable, not if there's a Nature paper or a cool science paper or whatever it might be. The third, there's a good article here that explains some of the work that's going on there, that we're doing there. The third one is, and I have to just touch on it because it's so prevalent, right? It's generative AI and large language model and foundation models that you've seen in the press, I'm sure. And I'm not going to say ChatGPT. There you go. I said it. So that's something you've all seen. But I want to just spend a few minutes explaining what that means for the healthcare domain, and particularly again the interaction between AI and the clinician who uses it and the patient who is intended to benefit from it, with all those boxes having to be checked to really claim that there's value in using this. Now, you might have seen this headline from very recently, end of last year, this chatbot that was released by OpenAI, GPT, took the, or a subset of the US medical licensing exam and passed, all right? It passed at a decent level, but it actually passed. So what that means is it answered the questions satisfactorily. Now, in March this year, the program took the test again and passed at expert level. That is something to really ponder about, right? There's people out there who study for years at length throughout the night and with their everything, give their everything, and then they pass this exam or they don't. And there's this tool that was trained for a month or two and does this thing, seemingly without any problems. What does that mean? That means we have a tool here that shows tremendous potential in, I do explicitly not say understanding language, because it does not understand language, but it's very good in interpreting language and responding and interacting with language in a way that resembles that of intelligent humans. Okay? Again, this AI does not understand any of the language it's being presented with when there's a question that it's being asked. It also does not understand any of the language that it produces. But the way it does it is very convincing to us because it passes the Turing test, right? So that's essentially an infamous test scenario that's been formulated. It goes like that: if a human can't distinguish whether they're interacting with an AI or not, that AI has passed the Turing test. And that's very much going on here, right? So we can use that technology to, for example, assist clinicians with all sorts of documentation, summary of reports, extracting knowledge from reports, preparing customized documents. But it's only working and can only be done if there's a human in the loop to double check that, right? It must not be trusted sight unseen. There is, and I'm not going to go into this, but the technology itself, I can't say this often enough, right? It is only as good as the data that it has been fed with when it was trained, with everything that was in that data, right? Correct information, incorrect information, inappropriate information, the whole shebang. That's being reflected in what it regurgitates. It does it extremely well to a point where, this has been called a stochastic parrot by very, respected researchers. It's very good in doing that, but it doesn't understand this, which is why we need to check. Someone with expert knowledge needs to check what comes out of it. We can use this, right? This technology to really translate between standards. The famous interoperability problem in electronic medical records is something that will be hopefully to some extent solved by this. We also can use this technology to dream up new things, because the fact that it produces stuff out of the blue means, well, sometimes factual correctness is extremely important, but sometimes it is not. For example, if we want to design a new drug target, something that might or might not work, and we have the whole clinical trial pipeline happening further down the road. Well, maybe in dreaming something up and not knowing why it dreamt that up, but then being able to actually validate that this drug target actually works is all we need. And this is, as a matter of fact, precisely what has happened in the world of drug discovery. Generative AI has been used for years before the current hype to do early stage target discovery design. You might have heard about AlphaFold, which is a deep learning tool that DeepMind has released 2 years ago, that's capable of predicting the 3D shape of any protein under the sun, and with that you know what that protein will do. And put that together now with the power of generative AI, you can now come up with new designs of proteins. You can predict the 3D shape that they will exhibit, thereby their functionality, and that, in essence, and this is brand new, allows you to bring clinical trial and validation stages down from what used to be 7 years to a little under 3.5 years, as shown by In Silico Medicine, who have just 3 weeks ago started the very first, world first, phase 2 clinical trial for a drug candidate that was completely natively discovered by AI, designed by AI, and to a large extent even validated by AI within 3.5 years from that initial conception stage. So that's real stuff, right? And this is where generative AI can really help a lot. I want to, as a sort of a controversial thing, just very quickly give you an example. Like, so people, like very respected researchers who published that in a peer-reviewed, top-notch journal, done the following experiment. They have taken a public database of questions that patients have put forward to clinical experts, and the answers that these experts gave, essentially a public repository, that contains hundreds and hundreds of such instances of questions and answers. They gave this to human experts and let them assess 2 things in these answers given by clinicians to patient questions: how well the content was to the point, and whether the information in there was correct and appropriate, and then also the degree of empathy with which these answers were given to patients. Now, they have then put the exact same questions to ChatGPT, let ChatGPT answer these questions, and had the same human experts assess the quality and the degree of empathy with which ChatGPT answered to these questions as well. Now, what was expected and what was always sort of the claim to fame for AI is that clinicians are important because they have this very specific relationship with patients that allows them to spend time with patients, and it's the interaction between patients and clinicians that play such a big role, and that's why the human is so important. Now, what came out of this is this. ChatGPT's answers weren't just rated very distinctly higher with regards to the information content, but also very clearly with regards to the degree of empathy with which they were delivered. Now, that gave a lot of people pause, obviously, right? And again, like previously, there's a lot of discussion going on around this study, right? What does this mean? Like, is an online conversation necessarily comparable to the interaction that a clinician has with a patient that they have gotten to know for years and years? Might there be a time factor? Someone typing something in online just wants to get rid of the answer and isn't necessarily connecting to the patient. So these are all valid points. But the point here is, this AI, as used in clinician-patient interactions through, for example, telehealth or virtual care environments, is capable of showing a very significant degree of empathy. And I'll not go into detail. I'll invite you to go through this when you look at the slides later. There's tests, like really standardized tests from the field of neuroscience and neuropsychology that, for example, determine where a kid might range on the autism spectrum. The Sally Ann test is one of them, and there's a scenario that kids are being, a very simple one being presented with, that essentially tests whether they can put themselves into another person's shoes. That's called theory of mind. Now, ChatGPT was presented with exactly that test scenario and passed in 95% of all those times. So, in other words, there's a standardized test, a neuropsychological test that is accepted widely as a gold standard for doing this kind of assessment, and this artificial intelligence system passes it. What does that mean? Is there intelligence, real intelligence going on under the hood that we can't quite fathom yet? Or is this just a very high-dimensional statistical probabilistic effect? We don't know. But it's interesting because the fact that we can pick up on this means that we can use it. Just like, for example, moral self-correction, which is the effect that's being observed when these models are made complex to a certain degree. which is when they exhibit very clear, normative concepts, socio-specific norms such as bullying, discrimination, these stereotyping, they start showing these features. Now, they also, and this is important, right? There's always two sides of this. They also can be taught, there's other techniques, they can be taught to avoid these behavioral features. So in other words, you understand that you make this model big enough, there's a risk of these behaviors, but then also you develop technologies and tools to counteract that, which means we can actually develop safer and better behaving and appropriate models knowing all these things. There's a fascinating, absolutely fascinating research going on at the intersection of engineering, computer science, and neuroscience right now that's not esoteric. We don't understand what it all means. Neither do the computer scientists understand what goes on under the hood exactly in these generative AI models, nor do the neuroscientists understand why these models, these AI models exhibit these features. But the knowledge of that these effects exist and how they result from architectures of these models can be used to build safer models for use in, for example, these telehealth and chat applications. There's a good paper from Eric Topo that summarizes a lot of what I just said here, right? So there's AI that we've seen for image recognition. There's AI that we've seen for, that we've talked about for chatbots, for patients. We've briefly touched on protein generation and drug design. It loops back to what I said at the beginning. We have reached a state where we can use AI to tackle all of these problems, right? And it is pretty straightforward to access these features of the AI and apply them to these problems. It's not connected to years and years of custom development of a specific model. We can take this stuff, and of course there's more work to do. I don't want to diminish the effort that goes into building efficient models, on the contrary. But it is much more accessible now. The type of data, the data modality that these models can handle, the problem proposition that they can address is so much more flexible than it was only like a year or a year and a half ago. So that's the realm we're entering into, and I invite you to have a look at that paper as well. Data is the juice that makes all this flow, right? So it goes into these models as training data. It is used to validate how well these models work, and at the end of the day, it's what these models are being presented when they're deployed. So the data is the one most important aspect of anything in AI. Right? Anyone who develops AI models will spend like 20% on developing the model and 80% of their time on wrangling data, right? Whatever it entails, from curating it to sourcing it to. So let's just speak about data for a second, which is so utterly important. And one aspect here is the ability to use data. What it depends on is the agreement between data owners and those who want to use it. In the clinical world, it's called consent, right? In the world of the arts, it's called copyright. That is something that needs to be absolutely observed and understood by anyone who's deploying, who's developing, who's designing AI solutions for anything. And it's tricky, right? Especially for these kind of models. And I will give you a very tangible use case, right? So with these generative AI models, you will have seen, I'm sure, that at times they produce inappropriate content, right? Now, of various degrees. And this has led to very controversial lawsuits where those who had actually created and produced that inappropriate data are being sued for that. Now, there is such a thing as the Section 230 Free Internet article, which essentially says that if I host on my social media page inappropriate content, I'm responsible for that, not the provider of that website. That's what essentially the companies who had been sued for producing inappropriate material using AI fell back to. They said, well, hold on, we are only using as an input to our AI models what others had created. And it goes through the sausage maker, but at the end of the day, we're not adding anything new to it, right? This is responsibility lies with those who we took the data from, not us. They did that until the first artists came up and said, okay, hold on. If that's how it is, and if you're not actually creating anything new here through your AI, you're just selling our stuff then, right? It's what you just only just repackage what we have created. So shouldn't we get a cut of the proceeds that you do with that? That pointed to a rock and a hard place situation, and it's clear that it has to be one way or the other. You can't be in between these two copyright situations. And it will be very interesting to see how this plays out. This is where copyright plays out, but it will absolutely be relevant to using information and data in the healthcare domain as well, where it's not just the copyright and the money and the commercial value, but also accountability, right? Liability. These things are important, which is why, and we're working on many of these projects right now, where ethical, responsible guidelines for implementing AI solutions in real-world solutions need to be worked out before you throw these things out in the open and just use that stuff, right? And this is something, regulation in this space is something that follows after technological progress and innovation. There's always this gap in between. It makes it very hard to navigate for a clinical service provider, for a clinician, for any sort of stakeholder really, to navigate the deployment and use of AI safely. And it's something that needs to be brought under control. Watch what the AuAI Act produces there. This is probably the leading regulatory framework, which will for the first time produce a legally binding framework for the use of AI, not just generative AI in general. And institutions such as the FDA, also the TGA here in Australia, have recently updated their guidelines on the use of AI for software as a medical device technology that tries to grapple with that. But it's everything but a solved thing, right? So this is a very tricky, treacherous area to go through. I'm not discouraging anyone from doing so, but I just wanted to highlight that besides the technical intricacies, and even in plain sight of all the great outcomes that you can achieve, safety, privacy, transparency, explainability, all of the ethical features of AI need to be built into the product development, design, and use process. That is just as important as cranking out top-notch papers and being a leading scientist and technologist. There's got to be that regulatory and responsible deployment regime being deeply ingrained into all you do. I wrote about this in 2 papers recently. There is also the World Health Organization, who has put out a seminal report on how to incorporate ethical principles in digital health solutions, especially so around AI. I invite you to read those. There's a couple other papers. Again, I threw those out there because I think the slides will be shared, so these are further reads. And there's also a book that, this is actually prefaced by Eric Topol, and which I wrote together with colleagues from the pharma world, which summarizes all of that and gives you a lot more food of thought and pointers on how to work with this in a pragmatic way, this being the incorporation of AI technology in clinical practice and use. Thank you very much for your attention. I'm very much looking forward to questions and to talking with you later.
Thanks, Stefan. Next speaker, Professor Helen Fraser, is the Clinical Director at St Vincent's Breast Screen and Breast Screen Victoria. Please give a warm welcome to Helen Fraser.
Thank you very much, Luan, and I'm delighted to be here. And thank you, Stefan, for your fabulous presentation. I've learned a lot, and thank you for the introduction into breast cancer and mammographic screening. So today, I think we'd all really feel that it's such an exciting time to be in healthcare. But at the very same time, and I'm speaking from the perspective of a doctor that's worked for 30 years in public hospitals, it's also an incredibly challenging time. You know, we see considerable problems across equity and access and costs of the healthcare system. And this is even more so as we emerge from the pandemic, and we're forever changed. So I do feel very excited when I reimagine or start thinking about healthcare, and that's because we've got this tremendous opportunity that can be leveraged through AI and many of the use cases that Stefan's talked about. And tonight I'm going to talk to you about breast cancer screening because that's kind of very dear to my heart. But it's also really interesting because even though it's a mature program, it's been operating for 30 years, it really could be an exemplar of the future of health. Because in the breast cancer screening program, the way the program's organised is that we interact with well people. And we do that through a lens of actually prevention, early detection and precise treatments. That's what we're aiming for. And we use data and digital platforms, and we will be using artificial intelligence as well, to enable us to really address the challenges that we have in screening, which are accuracy, experience and costs, and these in fact are the challenges across the whole of the healthcare system. So screening, population screening is really a microcosm of what we see in health. And you know, I think that's where the real promise lies for us to move towards a personalised screening pathway, and included along with that, which are the precision treatments for breast cancer, so that we can get to that ultimate goal which we're all aiming for, which will advance the human condition and really improve societal outcomes and healthcare for all, which is precision medicine and precision healthcare. So that's a sort of a broader picture of things, but what I'm going to talk to you about is the research program that I lead, which is called BREAKS, and it's building capabilities to transform breast cancer screening with artificial intelligence. And right at the outset, I'd like to acknowledge the tremendous support from the research partners that you can see on the slide there, as well as the team of researchers that I work with. Our vision is to reduce deaths from breast cancer and improve the woman's screening experience. So let's orientate to the problem first. Breast cancer is a major public health problem. So it's the most common cancer diagnosed in women globally, and it's the most common cause of cancer death in women globally. And we'd all be very familiar with the sobering statistic that 1 in 7 women will be diagnosed with breast cancer by the age of 85. And this year in Australia, we'll see over 20,000 women with a diagnosis of breast cancer, a new diagnosis. And sadly, around about 3,000 women this year in Australia will lose their lives directly as a cause of breast cancer. So it's a significant public health problem. We know that early detection of breast cancer, while the disease is not palpable, can't be felt, it's not symptomatic, and hasn't spread to distant organs or lymph nodes, and treatment confers significant survival benefits if it's detected early before it advances to extreme. And we also know that screening mammography or population screening, detecting cancers before they do present clinically, saves lives. And in Australia, we're very fortunate. We're one of just 27 countries globally, and Stefan's alluded to another one, Sweden. The European countries also have population screening that offers a national organised population breast cancer screening program. And in the program, women aged 50 to 74 years are actively recruited from the Australian electoral roll, but women above the age of 40 years are eligible to attend. And the screening interval is every 2 years. And around the country each year we screen about 1 million women, and that unfortunately has been lower during the pandemic. We're just now, as we emerged through the pandemic, starting to lift our participation rates. But what's really relevant to this audience and is really exciting for the use of technology in cancer screening is that we've been digital for a really long time. You know, we've had a digital detector to acquire our images for well over 10 years in the screening program, and that really helps us because, as we all know, we were looking at digital data, etc., for the development and creation of AI tools. So just a couple of other quick statistics from this slide is that since the program's inception in the early 90s, it's a 30-year-old program, we do see an improvement in survival of breast cancer. 5-year survival rates up to 91%. This isn't just attributed to screening, I need to acknowledge it's also attributed to improvements, considerable improvements in treatment for breast cancer. And women that do attend the Australian population screening program have a reduction in mortality or death from breast cancer of between 40 and 52%. But I think, even though these are good statistics, we can do better and we can leverage technology to do better. And what we're looking for is how do we take that next quantum step in reduction of death rates and improvements in 5-year survivals. And I think that data, digital platforms and AI have considerable opportunity and promise here. So breast cancer is very common. Population screening saves lives. Breast cancer screening is a really successful public health initiative, but screening has challenges. And before I take you through those in more detail, I think it's important to consider the pathway of a woman that goes through the breast cancer screening program. And following registration, where demographic information is collected from the woman, she will then have a screening mammogram, which are 2 views of each breast at right angles. And these images are QA'd and then presented to the radiologist for reading. And Stefan's alluded to this, but certainly in the Australian program, every single mammogram is read independently by a breast imaging radiologist, oftentimes subspecialty trained. And if they agree, that's great. But if they differ, it goes on to a 3rd radiologist for an arbitration read. So it's really quite time intensive and resource intensive. 95% of all of the women that come through screening receive an outcome of all clear, and they go back to routine rescreen in 2 years' time. 5% will go through to the assessment pathway, and at the assessment clinic, more images are taken, digital breast tomosynthesis, 3D imaging, ultrasound examination, oftentimes a clinical examination, as well as potentially a biopsy. And the outcomes at assessment is a routine rescreen, which is a benign or no significant abnormality outcome, or else a screen-detected breast cancer. And to give you an idea, we need to screen a lot of women to diagnose cancers. There's a low prevalence in the well women population. Across the whole screening population, we diagnose around about, at an aggregate level, about 6 cancers per 1,000 women screened. So that's the pathway, and it's relevant to technological innovations. So if we go now into the challenges of screening. So again, these aren't unique to screening, they're across the whole health system. Challenges of accuracy, experience and cost. And when we think about accuracy, mammographic interpretation is challenging. We're looking for tiny preclinical disease in a vast breast usually. So because of that, we have the 2 reader and the 3rd if they differ, that consensus model that I've talked about. But despite that model, every year around the country, we do recall about 35,000 women to the assessment pathway with an indication for cancer. And those women subsequently end up with a routine rescreen, all clear, which is really good news for them, right? But in the interim, they've had anxiety related to coming back to assessment. They've had potential morbidities from interventional procedures that they may not have needed, and there are considerable costs. So these are the harms of screening, and they're the false positives of the assessment. The other consideration are the false negatives. These are women that come through the screening program, have a normal screening mammogram, and in the intervening period, 2 years before they present for their next screening mammogram, they develop a symptom. It's usually a breast lump. They go to their GP sends for more imaging and a biopsy, cancer's diagnosed. And that's what we call an interval cancer, or the false negatives of the screening program. And importantly, these are fed back to us at screening for our review because they're reported to the cancer registry. Now, we'd like to see both of those scenarios reduce. When we think about the client experience, this is front and centre for us in the cancer screening program. We do have a flat participation, around about 55% of the eligible target audience, lower again during the pandemic. The service level, and I don't think it'll be too hard for you to think about this, but with that consensus reading model, is that time to results is, in the modern times, I think somewhat slow, up to 14 days for women to receive an all clear outcome. And that's a long time to wait for a normal result, and 95% of our results are normal. It would be wonderful to really reduce that. Also, the program's predominantly one size fits all, so it's not actually tailored to a woman's individual risk of developing breast cancer, and increasingly women feed back to us in the clinics, they know about mammographic density, they know about different imaging modalities, and they would really like their screening pathway to be tailored towards their individual risk. And the final consideration is cost. We have a really, the health dollar's strained, we all know that. It's an expensive program to administer. It costs around about $270 million across the country. The costs are rising. And we see an ageing population, an increasing incidence of breast cancer, and an increasing demand for our services. And coupled with this, we've got this situation whereby we have a workforce problem. So the College of Radiologists have predicted that in 5 years' time we just won't have the capacity to meet this demand. So you can sort of see all of these challenges can present really wonderful opportunities to leverage artificial intelligence in cancer screening. So the BRACS program is building capabilities to address these challenges. And I'll just read out our aim, which is to better use mammography with AI to prevent women dying from breast cancer in a way that improves their detections, lowers harms, reduces costs, causes less stress, and can be quickly put into practice. So it's a really ambitious aim, and we're about 2 years through a 3-year program. But we are really aspirational, and we're working hard to get there as best as we can. So when we think about those capabilities, there are 3 segments or 3 areas that we've been working hard on. And Stefan also said, and I agree entirely, that the most critical piece for us is certainly the data set development. Significant resources and time of our grant have been spent developing the capabilities for multimodal data, development and management, and establishing a fully grounded data set, which is critical for development of AI tools, and also establishing a data set in size and scale for generalisability testing, for us to be able to look at various segments or cohorts of the population and determine how the algorithm performs, not just at the aggregate level, but across the various cohorts. In terms of the next area that we're looking at, or we've been doing in parallel with dataset development, is the algorithm development. So we've been training and testing algorithms. I'll show you some slides about that shortly. We've tested the algorithm as a standalone compared to the radiologists in the program. And we've also done a large retrospective real-world cohort study where we have simulated, or we've done a retrospective digital twin, and we've simulated putting the AI reader into the screening pathway. And the final piece, which we're pushing into this now, is with prospective studies, is the human AI integration. And again, thank you, Stefan. Stefan alluded to this. What's it like to be human and interact with an AI interface? This is absolutely critical as the technology advances such that it's really getting close for prime time. It's the people side of things that's going to be a really critical dimension here. And that's by performing a randomised control trial and really evaluating explainability and the ethical considerations that Stefan alluded to. So I'd like to mention that it's, congratulations to Luan for having this Convergent Science Network meeting, because we are supported by a multidisciplinary team to do this work, and that is a really, really important thing. We have radiologists, breast surgeon, bioinformaticists, epidemiologists, data scientists, AI engineers, and we have a really fantastic group of postdocs and PhD students working for us. Understanding each other's science and language and perspectives is really important, and it's the conversations that we have at the intersections of these disciplines that propel us forward. They're oftentimes challenging. We get used to working in productive discomfort as we sort of talk and debate things, but that's what puts us at the cutting edge with everyone's perspectives of their view on, on how the technology can interact with screening. We've just recently incorporated into our group some social scientists. We have a philosopher and a bioethicist to help us really, think about all those ethical considerations. So I'm going to take you through the dataset development now. It does underpin all of the work that we've done. So the dataset's called ADMANI, Annotated Digital Mammograms and Non-Image Data, and currently it's around about over 4 million images, but we're adding another 2 million images to it as we speak. We've extracted another 2 years worth of data recently. But in here we see like over 22,000 really grounded, gold standard surgical histopathologically proven breast cancers. And just to put that in context, someone like me who's spent most of my career as a radiologist in breast imaging, that's probably hundreds of lifetimes of work. With the low prevalence of cancer across the screening population, to have the ability to interrogate a catalogue of validated cancers in the 20,000s, 25,000s is really wonderful. We also have those interval cancers, the false negatives as well. And attached to every image in population screening, we also have non-image elements, and they include everything from age, hormone replacement, symptoms, what happened at assessment, what was the pathology, were the lymph nodes involved, right the way through to linkage to the death register. Did the woman die from breast cancer? It's a really wonderful data set and a privilege to work with it. And I mentioned before that it was really well grounded. A couple of interesting things about the data. This is a look at the different mammographic or machine vendors in the population data set. And you can see there's some waves of vendors moving in and out. But over the last 10 years or so, we've seen about 6 mammography vendors in the program, and currently we have probably 2 that are getting towards market share. But this is really important for that generalisability testing, for instance, when we look to see how the algorithm performs, not only at the aggregate level, but across various machine vendors, because we want to know, does the algorithm perform better on a certain vendor? Is it agnostic, machine agnostic, and performs similarly over each of the vendors? And the algorithm does look like it performs well across all, because as you can see from those earliest times, which is where we ended up training the algorithm from data back at that time, it was exposed to images from a large number of machine vendors. And this is also helpful to have this granular information for when we come with quality assurance, if the algorithm's drifting or in fact fails, which is really a concern, that we can determine that quite quickly. We can look to see, was it because a certain screening site bought a new machine and the algorithm hadn't been trained on that machine, so it performed really poorly on it, and we can start to look at how we can address those challenges. The next segment of that circle is the algorithmic development. So we started out with 100 open source algorithms. As I say, we've had this very cancer enriched in silico data set to explore with. We did a lot of data augmentation as well, contrast adjustment. We took off the text from images. We didn't want any hidden stratification for the algorithm to learn on features like a side marker rather than a cancer in the breast, which is where we really wanted it to head, as well as cropping and changing the image sizes. So a lot of work initially there, and then we started to look at patch classification models, not the whole breast. Then we moved into global models. We did a fusion of both local patch and global, and we ended up with our best performing AI reader being an ensemble of 8 neural networks, and they're kind of listed there. But interestingly, 2 of the 8 are from a technique where both images are fused of the same breast, and the other 2 are algorithm architectures for explainability. And it turns out, and it does make good sense, that if the algorithm's able to help us explain the output of the system or interpret it, that it's also actually a very good classification algorithm. And this was the ensembled reader that we took to the real-world retrospective cohort study. Now, apologies, an ROC curve, don't worry if you're not familiar with these, we won't dwell on them because I'll just take you through and summarise what it's found. But these curves are used a lot to look at the performance of a screening test. And it's really looking at trade-offs of sensitivity, detecting a cancer when it's present, as well as specificity, detecting normal when the study is in fact normal, across all different thresholds. And if the curve that you can see on that diagram hugs that top left corner, that's the best test of all, but we never really get, or never ever get perfection in screening. But if you look at the insert there, you can see the dotted line, and that's the receiver operating curve for the AI reader. And sitting below that, or quite similar to it, is the weighted mean of the human reader, the individual readers across the state. And we've got over 100 readers that read for the state of Victoria. So we can see that the curve anyway performed similarly or just slightly better than the weighted mean of the individual radiologists. And other groups globally have found this as well, and in some of the papers that Stefan put up. But the important thing here is that red square. And that's the consensus outcome of that 2 reader and the 3rd if they differ. So what we can deduce from this is that the AI reader is not ready for standalone. Sure, it does perform similarly to an individual mean weighted average of the radiologists, but it can't beat that consensus where the 2 readers kind of gamify and war against each other, and a 3rd reader if it's required. And we'd see an uplift in sensitivity, but we don't lose any specificity, which is really important because we want to reduce those false positives. Other interesting things that we've found, not surprisingly, the algorithm detects a very strong signal for normalcy, or a normal study, and a really strong signal for cancer. So 95% of our screen detected cancers in that retrospective cohort, which was large, 500,000 women actually, probably the largest retrospective cohort globally at the moment, picks up the strong signal for screen detected cancer, 95%. But interestingly, in that red box, where the interval cancers, the false negatives are, the algorithm picked up 40%, or 40% of those interval cancers were in that uppermost decile of prediction for malignancy. And this is really, really interesting and feeds into our risk prediction work, because there's something that the algorithm's seeing that the human hasn't seen. And that's something that could be really helpful for us down the track to reduce those false negatives. The interval cancers, by the way, are often the high-grade, invasive, fast-growing cancers, what we call, in unfortunate term, the killer cancers. And those are what we really want to make some inroads with. I'm mindful of time here. I'm not sure how much longer I've got, but just thinking about generalisability testing, I mentioned by machine vendor, and we can also look here at generalisability by screening round. Is it the first visit or a second and subsequent visit, as well as age? And there were some interesting discoveries here. So when we looked by screening round, we found that the AI reader had much better specificity than the human. And from this, we can sort of really understand, and certainly being one of those readers, that the human really, really likes to have a prior round to compare to, a prior mammogram to compare to, because we're really very cautious, and we just want to make sure that we get great comfort, I guess, from looking at a previous X-ray to see if there's been any change, and we don't have that with round one. But the algorithm doesn't mind. It calls back a lot less women unnecessarily to assessment. But the corollary of that is when we come to women of increasing age that have come at 2-year intervals for many times, and there are prior rounds, we find that the human actually does a lot better with specificity than the AI reader. So from this, we can hypothesise that the human makes really good use of those prior rounds. And that's also pushing us into another area of investigation, which is to train an algorithm to be able to determine interval change between 2 X-ray studies, which is really going to be valuable for oncology imaging. Is a cancer growing? Is it smaller, etc.? And other groups globally are doing this work as well. So we then, after we looked at standalone, we've then looked at integrating the algorithm into the screening pathway. And this flow diagram shows what normally happens on the left there. In the middle there, you'll see the second reader replacement, where the AI reader's put in to take the place of the second reader. And the final one, which is a big ethical hurdle, but really quite compelling, but understudied, needs further development, is where the AI reader actually reads all of the mammograms first. And there's a rule in and a rule out. The AI reader rules out all of those very high confident normal scans, and they can just go straight to all clear. The AI reader also rules into assessment all the definitely malignant studies, so they can go straight into assessment, and we don't lose precious time as we evaluate what is looking like very much a definite malignancy. The middle band are read by the usual human model. But as I say, that's a higher ethical hurdle. The human can still stay in charge through quality assurance, looking very closely. But this one actually is a really interesting consideration. Not ready for prime time. So yeah, you've seen the ROCs before. This is just wanting to orientate you again mainly to that red square. That's the human consensus model. And then the green square, which you'll see in a moment in a bit more detail, is when the AI reader got put in as the second reader, and that's the overall consensus of it. The purple square is when the AI reader is the band pass, ruling in and ruling out. So this is the second reader replacement, and point you there to the green arrow. That green circle on the ROC curve is the threshold that we set for the AI reader integrated in as a second reader. And the green box is showing the consensus output of the AI reader integration with the sensitivity and specificity very similar to the human model. And we're kind of pushing to the space where globally, our group and others are just finding that we're really getting that integration up to the level of this consensus model. That there was some genius in that consensus model 30 years ago, but we're really starting to challenge it. And this is the band pass. So you can see the 2 thresholds, because there's a rule in and a rule out. And this one gave the best results of all. So in the purple box there, you can see, just marginal though, increasing sensitivity and specificity compared to the consensus which is the red box. But it wouldn't take long, and we've looked at the economics of this for you to understand that this one delivered considerable workload reductions in a really challenged workforce. So we saw reductions in workload required by around about 50% with this scenario. And hence what I'm going to call avoidable costs that could actually be put into other areas, increasing our capacity, screening more women, allowing more women to be screened. So the final segment, the human AI integration, And prospective studies are needed for this to look at that relationship between the human and the AI interface. And our group has some funding, and we're currently developing protocols for a randomised controlled trial, which will bring the AI reader into that screening pathway as the intervention. And we hope to submit to ethics towards the end of the year. And then the final stage is deployment with all of the quality assurance that's required. We've got a health economic evaluation going on as well. And the really critical piece, which is the bioethicist and the philosopher and their teams helping us to understand many of the considerations, like what will it take to build trust, not only for the clinicians whose work will be initially augmented but ultimately disrupted, someone like me. How do we interact with the AI interface? What will build our trust with it, as well as to the consumer or the clients? What does AI mean to them? What do they think about a machine reading their mammogram? What will it take for their trust to be developed and maintained? We know that trust takes a long time to develop, but as Stefan said, it can be lost instantaneously and very hard to rebuild. That's really important to us. So the three capabilities I talked about, that data and the data and AI capability, we've focused on improving image classification with AI readers, but we're also working very hard actually on developing a risk tool, which is better than our current risk tools. And we're doing that with multimodal data. We're adding some of those epidemiological factors like age and density, family history, as well as the mammogram. And we're fast learning and realise that the mammogram is actually a biomarker, and in fact can probably tell us more about a woman's risk of breast cancer than her DNA can alone. And ultimately we want to get to this personalised screening journey. I've got choice down there at the bottom, but choice is actually front and centre. What does the individual want? But we really would like to tailor their screening pathway towards to their risk of breast cancer, and we can do this by changing screening intervals. Maybe someone that has a very, very minuscule risk may not come to screening for a while, or may have an interval of 3 years, whereas the high risk woman may actually have more frequent screening, at least annually, with different modalities. We've got more in our toolkit now than we had when screening started 30 years ago. We not only have 2D mammography, we've got 3D mammography, we've got contrast enhanced mammography, we've got some really fantastic ultrasound, and we've got MRI, which is the most sensitive test of all. If we designed screening today, it would probably be quite different from what it was 30 years ago. So finally, we've come to the end. We've been talking about the future, but I'd like to really take us way back 2,400 years or so to the time of Hippocrates, the father of modern medicine. And all doctors do sign up for or take the Hippocratic Oath in some form. And I think that these quotations which have been attributed to Hippocrates are really relevant, and they're really a North Star for us. I won't read them all out, I'll let you do that, and certainly in the interest of time, but to me they resonate and they're so insightful, because the first one, for instance, is that scenario of high consequence decisions at scale. It is such a privilege to work in healthcare, and it's just so important that as we develop and learn and create AI solutions, that they are responsible and they're safe and fair for all, and they have appropriate guardrails, etc. So that's a really critically important thing. The next quotation speaks, I think, to risk prediction. Know the past, think about what's happening right now, and what then can we forecast will happen down the track and in the future. And the final one is really pushing us into that era where we all want to go to, of precision medicine, precision healthcare, which, this one I absolutely love, because it's so important to know the person's individual biology and individual preferences, rather than all the focus that we oftentimes have on the disease itself. So on that note, I'd like to thank you very much for your attention. Thanks, Stefan.
Time to have some questions from you. We have time for a couple of questions.
The question is Dr. Fraser. So with training AI or assessing its impact, can you, if you separate the type of tumours into sort of microcalcifications, a lobular cancer in a low density breast and a lobular cancer in a high density breast, can you see the difference in performance?
Yes, that's a really great question. Thank you very much for that. And the answer is yes, but we're so early on that journey. But because of the nature of the data set, we know the different types of pathology of all of the tumours, and we know the imaging features as well. So we did find, as I mentioned, that the AI reader performs differentially on various subtypes of cancers and various breast compositions. So it's an area that we do need to study a lot more, but I think it's a really promising area because as you allude to, like the invasive ductals and certainly the invasive lobular, and in fact especially the invasive lobular cancer, is a hard cancer for radiologists to pick on mammography. It's an area that we really do need support with, and maybe AI can help us with that, detect those lobular cancers specifically better than we can.
Also, as a follow-up, if a diagnostic radiologist knows that the patient is BRCA1 or BRCA2 positive, they sort of look more closely. Is it possible to get the AI system to look more closely if it knows that sort of background?
Yes, so those sorts of metrics, I mean, the BRCA carriers are outside of our population screening program. They'll go into a familial cancer clinic, but sometimes various situations mean that a woman doesn't know that she's a BRCA carrier, so she does come to screening. But that's one, would be one of the variables that feed into our risk tools that really would, increase that risk, and coupled with the image can really help us to identify. And the other thing about, which I'm sure you'd know about, the breast cancers that the BRCA mutation carriers develop, they often look very benign. They're often rounded, smooth margin, encapsulated, and they can look like benign disease. So again, that's an area that radiologists can not make the correct diagnosis. But I think an AI tool, knowing it was a BRCA mutation carrier, and the imaging findings, and when we did see it, or when a circumscribed lesion was seen, it wouldn't be overlooked, especially with that history. Thanks.
Thank you for the very nice talk. I was just wondering, because DREAM was rather not successful in the endeavor, and you're trying to attempt the same, but with more data and higher quality data, if I understand. So that's a competitive advantage, if I got it right. What I was wondering, if you also tried to find a sweet spot where your performance is saturating. So for example, if you do like a dropout and you remove 10% of the data, 20%, 30%, 40%, when you see what your AI performance is dropping. I think this could be very interesting, because that could be like a percentage you need to have to build a good classifier. And you could do like a bootstrapping, so that you build multiple classifiers and that you build multiple digital experts and try to build a consensus across them. Because that could maybe also be like your second or third radiologist. And I was just wondering if that could be maybe giving you a little bit of an competitive advantage with your data set and what you could do.
Wow. When are you coming to join the team? My background isn't data science, and I can understand in part what you've mentioned, and I'd love to explore it further. I know our team are looking at things like that, but it sounds like a really exciting opportunity because it's such a wonderful data set to work with, and I think there's many opportunities. That's part of the frustration. There's so much to do with it. It's actually sort of getting the time and the ability to do it. So I hope we might be able to connect and talk further with that, if that's okay.
Yeah, absolutely.
Thank you.
I mean, also algorithmically, I guess most of the previous work was based on convolutional neural networks.
Yes.
But if you have sequential models like LSTMs or transformers,
Yes.
I guess you can also get the time components that are encoded, and that would be also quite interesting.
Yes, absolutely. Thank you.
Question for Professor Fraser. Thank you so much for your research. I'm fascinated to know if you've come across any data with AI and kind of mining what may contribute to, let's say, lifestyle factors that put women at risk of breast cancer in the first place.
Sure. It's a really great point, and I didn't really have the time to touch on that, but there are a number of modifiable risk factors that are in breast cancer that are really well known, and we've got great opportunity to really think further about them. And one of them, front and centre, that I'm sure you've heard of, is alcohol. But when we go out and survey the women that come to the program, many of them don't actually know. And in fact, I've been quite surprised to read the literature myself that even a small amount of alcohol increases risk of breast cancer quite considerably. But there's also weight, and inactivity. There are some risk factors that can't be controlled necessarily, like the number of children you have and whether you breastfeed or not and when you had those children. But yes, there's a really good piece of work to do in that whole prevention of disease. That's ultimately what we'd like to do, and the early detection, or to attenuate the disease, because that's how we'll make that next step change in reducing deaths from breast cancer and really improving outcomes. So yeah, we don't capture a client's alcohol intake at the moment, but we do have access to things like weight, and we're actively thinking about how we can really, we don't want to disencourage anyone from coming to screening if we start to interrogate them about, things like alcohol, but it is such an important risk factor. And one of the screening services in Victoria, Maroondah Breast Screen, have an alcohol intervention, a study that is underway at the moment now with really interesting results. And the women are really, really recognising and enjoying might be the wrong word, but they're very happy to interact with questionnaires about alcohol and learn more about it and know that it can increase their risk of breast cancer. Thanks.
Thank you both for talking. If I can ask both of you, I hope that's allowed. Just keeping in mind the shortages in healthcare and the obvious needs and shortages in workforce and that kind of thing, so the potential of AI there in helping with that, but then also the dangers that both of you touched on in terms of building trust and losing it very quickly with going too quickly. There's obviously a balance between when we go too quick with AI and technological interventions in healthcare and then going too slow and leaving potential benefits on the table. How do you think we're going in terms of balancing that? Whether we're being too fast on applying new technology or being too slow when it comes to AI?
Yeah, that's a great question, because I think, so one of the things to realize is that bringing any of this innovation into real use is more a behavioral change exercise than a technology translation exercise, right? In that sense, I think the degree with which we provide programs to educate, to do upskilling, to build capacity among the clinical workforce, there's great ones out there, but I think that's where we need to get much better, right? I think there's much more discourse around technological innovation and high-level pitches as to what's possible in terms of bringing this out, and too little effort in terms of taking the consumers and the users along. And by taking along, I also mean not just presenting them with the ready-made solution, throwing it over the fence and saying, yeah, here it is, the solution to all your problems. It starts actually at the conception of these AI tools, right? It starts with selecting whose data you use. It starts with consumer-centric design, in actually taking those who you intend to use on the journey right up front. And that goes all the way to, during residency, there should be AI-specific components already, right? And it maybe even earlier, right? It goes into, taking graduate students and others along. And it's not just the academic world. I think, and I salute Luan for organizing events, free events like this, right? I think we need to do, as scientists, we probably need to do a better job in taking the broad public along with this as well, because only with that consensus can we then at the end of the day realize these efficiency gains, for example, or increased value. So my answer is we are too slow and not engaged enough in educational and capacity building exercises than we should be, compared to how fast we push the technology ahead.
Thank you. I'd like to thank Helen and Stefan for their commitment to be here this evening and to share their work, their ideas. I want to just thank the network sponsors. They make these events happen. The sponsors' contribution makes these events available to you at no cost. And I think I'm very proud that we've, again, maintained that for 15 years. So I'd like you to join me in thanking our sponsors. Thank you very much.